let's take a look at the intermediate value theorem. We'll prove this, and then we'll take a look at a really quick example that maybe makes use of the intermediate value theorem. All right, so what does the intermediate value theorem say? Suppose that f is this function that goes from a closed interval a to b to the real numbers. It is a continuous function. Then f has the intermediate value property on that closed interval. Right? So what is the intermediate value property? So the intermediate value property is that if k is any value between f of a and f of b, right? So k is any value between the function value at the two endpoints, then there has to exist a point C in the open interval. It has to exist a point C between A and B that's not at those endpoints that has a function value that is equal to K. So for every choice between f of A and f of B. Let's see if we can prove this. So let K be a number between f of A and f of B. If f of A is less than f of B, then we can apply lemma 5.3.5. Right, so what does lemma 5.3.5 say? And so that's the one, the lemma we proved in our last video, right? So whenever we have this continuous function with f of a being less than 0 and f of b being more than 0, there has to be a point somewhere in between where f of c is equal to 0. So we can apply lemma 5.3.5 to the continuous function. To the continuous function. G. So we're going to build this other secondary function. So we apply the lemma to this function g given by g of x equals f of x minus k.
I don't know that.
Then g of a is equal to f of a minus k, which is less than 0, and g of b is equal to f of b minus k, which is more than 0. Thus, there exists a c in the open interval from a to b such that g of c, which is equal to f of c minus k, there has to be this point c in that open interval that's equal to 0. That is, f of c is equal to k. If, on the other hand, we have f of a is bigger than f of b, we can do a really similar argument. This similar argument applies to this function let's call it h of x equals k minus f of x. And so in either case, we end up with some value, some number c that is between a and b that has an output of k. Right. So can we use something like the intermediate value theorem to prove that a function, an equation, has at least one real solution? So that's what we're going to do. We want to prove that cosine x equals x that has at least one real solution. There's some choice of x that will give us equality between those two sides of that equation. So let's let f of x be not just cosine x, but we're going to move all of this to one side. So let's let f of x be cosine x minus x. We might observe that this is a continuous function. So we do have a continuous function. Also note that f of 0, if we plug 0 into this function, in for x, cosine of 0 is 1. So we have 1 minus 0. So f of 0 is 1, and f of pi over 2. Cosine of pi over 2 is 0, so we have 0 minus pi over 2. So f of pi over 2 is negative pi over 2. So we make those observations. Thus, by the intermediate value theorem, there exists a c between 0 and pi over 2 such that f of c has an output of 0. So f of c has an output of 0 that is up here, f of x. So there's some choice that has this that gives this an output of 0. Therefore, cosine x equals x has at least one real solution. All right. Next time we'll take a look at uniformly continuous. What does that mean, and how does that differ from just a continuous function? All right. We'll talk to you guys next time.